Section 1 Introduction. In this paper, we're exploring the notion of weak learners. These are classification systems that can deliver better than random results on a specified set of training data. This concept became a key stepping stone in machine learning because it was discovered that weak learning could, through a process called ensembling, be transformed into much stronger classification. This led to the creation of boosting algorithms, which have proven to be very effective, especially on table-form datasets that do not exhibit the same pattern structure as visual or language tasks. Parallel to this, large language models, LLMs, built on transformer structures have recently been the go-to in many natural language domains. LLMs can be fine-tuned to specific data for different tasks. Additionally, they have also shown to perform well with zero-shot or few-shot learning, where the model can learn from a small amount of data or even from a single example. In this study, we're trying to link these two research areas. We're curious to find out if LLMs could also function as weak learners in a boosting setup, especially with tabular data where boosting methods are often used. Our research confirms this to be true. By converting tabular data into a text format and guiding LLMs to summarize a selected group of examples from the data, we can generate a summary of these examples. This summary then serves as a template or prompt for classifying tabular data, effectively achieving the goal of weak learning. This method allows us to include a set of LLM-generated weak learners into a boosting system. We have found that this approach performs well in numerous situations. It surpasses the performance of zero-shot, few-shot classification, and even the summaries generated by LLMs from a single example. Moreover, we achieve this without having to retrain or fine-tune the LLM, relying solely on effective prompting. Our study also shows that in certain areas, especially ones with very few examples, our approach can outdo traditional tree-based boosting and LLM fine-tuning techniques. The effectiveness of this method will likely improve as LLMs evolve and become more capable. To summarize, our research underscores the potential for using LLMs as part of a larger machine learning system. Section Summary. The paper explores the possibility of using large language models, LLMs, as weak learners in a boosting framework for tabular data classification. By converting tabular data to text form and using LLMs to summarize a set of examples, a template or prompt is generated for the classifier. The resulting approach outperforms zero-shot and few-shot classification, as well as LLM-generated single-shot summaries, without any retraining or fine-tuning of the LLM itself. The approach can even outperform traditional tree-based boosting and LLM-based fine-tuning methods, particularly on domains with very few examples. Section 2 Related Works. Let's discuss some related works in this field, especially focusing on deep learning approaches for tabular data and the concept of prompting with large language models. Tabular data, which is essentially data organized into columns representing various attributes, is quite common in machine learning applications due to its versatility. But this flexibility comes with a trade-off. Unlike text or images, tabular data doesn't possess an intrinsic structure, making its processing with deep learning more difficult. Also, it's usually domain-specific with a relatively smaller size, hence traditional deep learning techniques, which work well on large, high-dimensional datasets, aren't very effective. However, of late, there has been growing interest in using deep learning for tasks associated with tabular data, like data integration, imputation, semantic parsing, and even executing SQL queries. Deep learning models have also shown success in tabular data classification by minimizing loss functions. Our work differs from these approaches as we explore the use of large language models, LLMs, for classifying tabular data without fine-tuning or constructing a new language model. We posit that many tabular datasets can be translated into natural language, making text a practical representation for tabular data. We've observed that LLMs can convert tables to text using only prompts, a feature we've leveraged in our method. Once the tables are converted into text, our classification algorithm engages with existing LLMs solely through prompts. This approach results in a level of separation between the actual language model and the learning procedure. This could be beneficial for various applications as there's no need to access gradients or parameter updates. Prompting is a process where we provide initial text or instructions to guide a language model's responses. The advancements in LLMs have introduced new possibilities like chain of thought reasoning, zero-shot reasoning, compositional problem solving, and self-improvement, leading to the wide use of prompting across various natural language processing tasks. But there's a catch: LLMs interpret prompts differently than humans do. Hence, prompt tuning, which involves carefully crafting prompts, becomes crucial for getting accurate and pertinent outputs. Fundamentally, prompt tuning is an optimization task aiming to find the optimal prompt for a specific task. Even though many approaches recommend gradient-guided search for optimizing continuous prompts instead of language tokens, this method can be restrictive, especially as LLMs grow in size and their access becomes more API-based. Our method aligns more with discrete search strategies, given that LLMs can auto-generate prompts. In our approach, we prompt the LLM to summarize the tabular dataset. This summary then serves as a prompt for the LLM to make predictions, as it embodies knowledge about the dataset. A series of such prompts summarizing different data subsets can be seen as weak learners in a boosting procedure. Section summary. Tabular data lacks the inherent structure found in images or text, making it challenging to apply deep learning to them. However, recent interest in applying deep learning to tasks related to tables has emerged, including data integration, imputation, semantic parsing, and even running SQL queries. The authors propose using language model-based learning, LLM, to classify tabular data without fine-tuning or building a new language model, by prompting the LLM to summarize the tabular dataset, which in turn acts as a prompt for making predictions. Section: Boosting. Boosting is a popular strategy used to enhance model accuracy by merging a set of basic learners. This is the basis for several widely recognized algorithms such as AdaBoost, gradient boosting, and stochastic gradient boosting, among which the XGBoost library is a particularly popular tool. In prior research closely related to R's, large language models, LLMs, have been incorporated into AdaBoost for tasks in natural language inference. This was achieved by training a multi-layer perceptron, MLP, projection of the final hidden state of a particular token. Our approach, however, distinguishes itself in two major aspects. First, we avoid the complications of learning additional parameters and steer clear of using gradients, eliminating the need to access the model's internal states. Second, we focus on condensing knowledge into what we call a summary representation, instead of storing it in parameters. This strategy not only enhances the interpretability of the model but also makes learning a process driven strictly by prompts. This is particularly useful for small tabular datasets, where the embedded knowledge within LLMs can significantly facilitate the learning process. Our methodology, which we name summary boosting, revolves around using LLMs to generate basic learners. These learners are then incorporated into a boosting framework. The central learning process involves using a language model to create a summary of specially chosen samples from the dataset. These summaries then act as prompts for making predictions on new examples. An ensemble of these summaries is built using boosting, which then makes the overall predictions on new data points. Working with LLMs and tabular data requires a step of data conversion, converting record data into natural language descriptions. Traditional methods like template matching, where attribute values are filled into predefined templates, often yield descriptions that differ from how humans might describe the data. Manual template designing can also prove challenging, depending on the dataset. To navigate these hurdles, we propose using LLMs as a more fitting solution. As shown in the included figure, we can generate data descriptions with little effort by providing the LLM with the dataset's information, usually available as metadata for tabular datasets, and a textual representation of the record data, such as parsed JSON. We ensure that these descriptions can function both as training data and query inputs by combining the feature descriptions with the target label using a separator token. We've found that descriptions generated in this way by an LLM often outperform those from a template. A major challenge we encountered was the effective encoding of numerical attributes. Simply including numerical values in the descriptions can degrade performance in subsequent learning tasks. To tackle this issue, we group all numerical features into percentiles and descriptively encode them as low, medium, and high. After comparing the performance of several such methods, we found that the data descriptions could be automatically generated with minimal manual intervention. Section summary. Boosting is a technique that combines weak learners to create a strong learner, and commonly used. Algorithms include AdaBoost, gradient boosting, and stochastic gradient boosting. The paper proposes a new method called summary boosting, which uses large language models, LLMs, to generate weak learners and create a summary of chosen samples from the dataset. The data descriptions are generated automatically using LLMs, which perform better than templates, and numerical attributes are encoded descriptively as low, medium, and high. Section 3.2 Weak Learning via Summarization. We're going to delve into a method we've termed weak learning via summarization. Typically, when it comes to few-shot learning with extensive language models, or LLMs, the common technique involves using a handful of demonstrations of the task you want to carry out. These demonstrations act as prompts, following which the model generates a response. For example, In a few-shot scenario, you might present descriptions in everyday language to the model and ask it to make predictions on new instances. However, this approach may not be the most effective when dealing with tabular data, where you have many data points that cannot be easily integrated into the LLM context. We've noticed that simply cramming more examples into the context doesn't necessarily lead to better performance, a fact highlighted by our graphical representation, figure, right bottom. Moreover, managing weighted distributions over examples, as required in boosting methods, proved to be a complex task. These observations urged us to consider alternative approaches to weak learning via LLMs. Our proposed solution is to use summaries of a group of examples. This can serve as a powerful learning proxy for models, as summarization naturally prompts the extraction of key information from the data. Here's how it works. We start with a set of data descriptions. We then summarize this data using the LLM, for instance, by bringing together a list of examples in natural language and adding a TLDR, or too long, didn't read, prompt. This summary then acts as a hypothesis, providing an explanation for the data. The LLM uses this summary, or hypothesis, as a prompt to perform inference, instead of using the raw data description. This process is demonstrated in one of our figures. However, these generated summaries can occasionally be imprecise. To combat this, we create a fixed number of summaries and select the one that results in the smallest validation error rate. If there's a tie, we opt for the one with a higher training error. That is, the one with a smaller gap in generalization. There are several ways to construct these summaries, but as we'll show in section, simple methods like the TLDR approach often perform just as well as more complex alternatives. Section summary. The traditional few-shot learning method with large language models, LLMs, may not work well with tabular data, and increasing the number of examples in the context may not always improve performance. To address this, the authors propose using summarization of a collection of examples as a proxy for learning models based on some number of examples. By generating a fixed number of summaries and selecting the one with the smallest validation error rate, the LLM can use the hypothesis to perform inference instead of the raw data description. Section. Weighted cluster sampling. We're addressing a challenge with existing language learning models, LLMs, where they can't summarize the whole dataset due to context size limitations. Plus, boosting methods require us to deliver weaker learning elements on weighted data samples to focus on more complex examples. So, we're introducing a strategy that uses only a select, representative portion of the dataset, the size of which is decided by the maximum context size and data descriptions. To pick this selective subset, we use a method called weighted stratified sampling, with clusters defined by language embeddings, or language-based representations, of each data description. These language embeddings are generated by a tool called GPT-3. We further use a process called hierarchical agglomerative clustering to identify clusters within these embeddings. This process can consistently create weaker learners and can perform better than random guessing under specific distributions. Next, we employ the AdaBoost algorithm to create a diverse group of these summary-based weak learners. AdaBoost works by fitting a sequence of weak learners onto repeatedly modified versions of the data. The process occurs over multiple rounds, with the weight of training data points being adjusted based on the training error. For any new data point, the predictions from classifiers across all rounds are aggregated through a weighted majority vote to deliver the final prediction. We use the error on a holdout validation set to determine the number of rounds. In this method, the summary function condenses the examples in the prompt as previously discussed. Each summary acts like a hypothesis that can classify new data. But unlike the earlier process, where we resample multiple times to find the best learner, here, the boosting process stops as soon as a summary with an error rate better than random guessing is discovered. We use a method called cluster sampling to select a mini batch of examples that fit within the LLM's maximum context length. For an in-depth understanding of the time complexity of this method and the full version of our boosting procedure that can be applied practically, refer to our appendix. Section summary. The authors propose using a representative subset of the dataset for summarization, selected through weighted stratified sampling using clusters of language embeddings generated by GPT-3. This process consistently produces weak learners and improves upon random guessing. The AdaBoost algorithm is then used to produce an ensemble with these collections of summary-based weak learners, where each summary can be treated as a hypothesis that can classify new data. Section 4 Experiments. In Section 4, we undertake a series of experiments to put our hypotheses to the test. These experiments are primarily run using OpenAI's GPT-3 API. For the sake of diversity and comprehensiveness, we draw from 18 different datasets, which are a mix of collections from the UCI database and OpenML. Our key ally in these experiments is the Curie version of GPT-3. We decided to employ Curie, which boasts 13 billion parameters, chiefly due to its cost-effectiveness for large-scale experiments. The methods we evaluate include 1. Zero-shot. Here, we provide the language model with a description of the data and prompt it to complete the answer. More details are available in the appendix. 2. Few-shot. In this method, we give the model a handful of descriptions from the training data, each tagged with the correct label. We then ask the model to infer the label for a new data description. To maintain uniformity, we use about 15 examples for each dataset. The appendix offers a more in-depth look at this setting. 3. Summary. This is a technique we developed ourselves. We generate a series of summaries using a range of data descriptions. We then choose the summary that generates the lowest validation error and use it as the context to prompt the model to provide an answer for a new data description. 4. Summary boosting. We build on the summary method by incorporating it into an AdaBoost framework. We also wanted to see how our method stacks up against some commonly used techniques for dealing with tabular data that don't involve prompting. These include 1. KNN. For this baseline, we initially transform the data descriptions using the GPT-3 embedding API. We then employ the k-nearest neighbor algorithm to categorize a new data description. This method offers a basic demonstration of the amount of task-related information that can be obtained from the basic output of language learning models. 2. LIFT. The Language Interfaced Fine-Tuning Method, or LIFT, fine-tunes the language model with data descriptions and corresponding labels in a zero-shot setup. 3. TabPFN. This method involves a transformer-based architecture, which runs a Bayesian inference on all the data points in the training and testing set simultaneously. 4. XGBoost. The Extreme Gradient Boosting Method, or XGBoost, is a well-known, regularized gradient boosting algorithm widely used for tabular data. In the interest of robust testing, we use a 50-10-40th split for training, validation, and test sets respectively, across all methods and datasets. Each experiment is run thrice using different random seeds. The results of these experiments can be found in the table included further in the document. Section Summary. The authors conduct experiments using OpenAI's GPT-3 API on 18 tabular datasets from UCI and OpenML. They compare several methods, including zero-shot, few-shot, summary, and summary boosting, against popular baselines for tabular data. The experiments are repeated for 3 random seeds and the results are shown in a table. Section 4.1 Analysis of Prompting-Based Methods. Section 4.1 Analysis of Prompting-Based Methods. We observe that for test performance, there's a general trend from our findings as shown in the table. This performance seems to enhance sequentially, starting from zero-shot, then few-shot, summary, and finally peaking at summary boosting. Firstly, contrary to what is mostly seen with large language models, LLMs, being used for zero-shot reasoning, we found that these LLMs don't possess enough inherent knowledge to predict correctly without any supplementary information. This explains why zero-shot performed poorly across all datasets. This tells us that learning from the data is crucial and that the LLMs, unlike other tasks, do not have sufficient built-in knowledge to succeed in zero-shot tabular data classification. To address the insufficient prior knowledge issue in zero-shot, we employed few-shot in context learning, few-shot. We hope to find out if the extra information provided could aid in making improved predictions. As we anticipated, few-shot consistently enhanced the test performance on all datasets, except for visualizing hamster and wholesale customers. This suggests that the additional information is crucial for LLMs to be effective on tabular datasets. Now, instead of just stacking examples within the prompt in few-shot, summary takes these examples and distills knowledge from them. We observed that summary consistently improved upon few-shot across all datasets, except for Haberman survival and wholesale customers. This suggests that summarizing is a potent strategy for enhancing few-shot performance and has the potential to be applied to other tasks using LLMs. Finally, in every dataset we tested, boosting with summarization consistently outperformed all other prompting-based methods. This backs up our hypothesis that LLMs combined with summarization could be a great candidate for generating weak learners in the boosting process. Section 4.2 Comparison to other tabular methods from the data in our table. We also noticed that LLMs face difficulty when reasoning about continuous attributes without fine-tuning. This was particularly noticeable on datasets such as glass, wine, iris, and vehicle. When the datasets have a high number of continuous features, the performance of summary boosting could be notably worse than other methods, such as LIFT or XGBoost. This might be because LLMs are not as effective in quantitative reasoning without fine-tuning, something that future LLMs might be able to overcome. While k-nearest neighbors, KNN, is a relatively basic benchmark, it surprisingly performs well on some tasks such as wholesale customers, stat-log heart, E. coli, and wine. This underscores that LLMs possess an impressive amount of generic prior knowledge about the world compared to methods like XGBoost, and this knowledge alone can sometimes produce satisfactory results. Lastly, we noticed that summary boosting performs extremely well when the size of the dataset is quite small. This is logical since the advantage of using LLMs as weak learners is that they hold a large amount of generic pre-training knowledge about the world. When the dataset is large, this prior knowledge may become less relevant, and other methods such as fine-tuning could become more competitive. Section summary. The analysis of prompting-based methods shows that zero-shot performs poorly on tabular datasets, highlighting the necessity of learning from the data. Few-shot consistently improves test performance compared to zero-shot, and summary further improves upon few-shot on all datasets except for Haberman survival and wholesale customers. Boosting with summarization consistently outperforms all other prompting-based approaches, making LLMs a good candidate for creating weak learners in boosting. However, LLMs have a hard time reasoning about continuous attributes without fine-tuning, and summary boosting may perform worse than other methods such as Lift or XGBoost on datasets with many continuous features. KNN performs surprisingly well on some tasks, highlighting the remarkable amount of general prior knowledge LLMs have about the world. Finally, summary boosting performs well on small datasets due to the large amount of generic prior knowledge LLMs have from pre-training. Section 5 Ablations. In Section 5 of our research, we conducted various experiments and studies to optimize our methodology for generating an effective weak learner through summarization. We found that it was crucial to pinpoint the right configuration that would lead to superior summaries. To achieve this, we performed several ablation studies on our summarization method, with the goal of determining the optimal hyperparameters that could yield a proficient weak learner. One key area we focused on was the preprocessing of continuous attributes. We tested numerous encoding techniques for these continuous features, including strategies such as binning, percentiles, and standard deviations. We ended up choosing an approach that involved explaining the features using technical language and assigning terms like low, medium, and high to each level of binning, as shown in the top right of the associated figure. Our findings revealed that this binning approach was the most effective for comparing examples and creating high-quality summaries. After fine-tuning the hyperparameters, we found that using 5 distinct bins was adequate for identifying differences in the continuous values. You can find more details on this in the appendix. We also wanted to establish whether our language learning model, LLM, leverages prior knowledge for its inferences. To test this, we performed an ablation study where we masked the attribute names and used a generic template that read, "This example has features F1 equals, F2 equals, and so on." The second figure from the left presents the results of this study. We found that when the true names of variables were used in the data descriptions, the LLM performed better at few-shot learning compared to when we used placeholder names. This observation confirmed that the LLM indeed makes use of its pre-existing knowledge of variables when making predictions. We were also interested in how the size of the model influenced its performance. To understand this, we compared the summarization performance of two variants of the GPT-3 model, the GPT-3 Da Vinci, with 175 billion parameters, and the GPT-3 Curie, with 13 billion parameters, across 5 different datasets. Our findings, as depicted in the left figure, were rather surprising. We found that the larger model did not consistently outperform the smaller one. We carried out a similar comparison with the ChatGPT model and discussed the impact of reinforcement learning from human feedback, RLHF. Lastly, we investigated how the model's performance scaled with an increasing number of examples. The bottom right figure displays the behavior of the few-shot learning and summarization techniques as the size of the support set, i.e., the number of data descriptions that are summarized, varied. We observed that few-shot learning performance peaked at a medium context length and declined with more examples. Conversely, summarization performance improved with a larger dataset, which is the more preferred behavior. Section summary. The authors performed ablation studies to identify the ideal settings for inducing high-quality summaries. They found that binning continuous features with quantifiers such as low, medium, and high was most effective for generating high-quality summaries. The authors also conducted an ablation study to demonstrate the LLM's utilization of prior knowledge and found that using true variable names in the data descriptions leads to superior few-shot learning performance compared to using dummy names. Additionally, They studied how the behavior of few shot and summary change with different support set sizes and found that summary improves with more data. Section. Ordering of examples. In simpler terms, what we are discussing here is the impact of several factors on how our machine learning model generates summaries. One of these factors is the order in which we present the examples to the model. There are two ways to do this. The first is to present examples in a random order, and the second is to group examples by their classes before presenting them. When we tested these two methods on 4 different datasets, we found that they don't significantly affect the results. As a result, we decided to use the random presentation method in all our other experiments. Next, we considered the prompts we used to ask our model to generate a summary. For simple datasets like iris, a basic prompt like, "Give me the gist," worked fine. However, for more complex datasets like vertebra column, we needed to use more detailed prompts. Despite the difference in complexity, both types of prompts were equally effective. Consequently, we chose to use detailed prompts in all our other experiments. As we delved further, we also compared 2 strategies for drawing inferences from data. The first approach is what we call a prefix prompt. For instance, this flower will be classified as. The second method involves a step-by-step reasoning process. For example, let's think step by step. Surprisingly, we didn't find a significant difference in the effectiveness of these 2 strategies. However, we noticed that the prefix prompt method often finished the task with less computational effort, and therefore we decided to use this method for all other experiments. In another aspect, we compared the effectiveness of using text generated from a template versus text generated by the GPT model. We found that text generated by the GPT model consistently achieved better results. This might be because this text more closely follows the natural pattern of human language, which makes it more useful for inference using machine learning models. Finally, we observed the impact of cluster sampling on the performance of the machine learning model. Cluster sampling is a method where we select a representative set of texts that can generalize better. This method reduced validation errors more quickly than random sampling during the learning process. Although it might require more rounds of sampling to create an effective learner, cluster sampling tends to converge faster than random sampling. However, if given enough rounds, the performances of both these sampling methods don't show a significant difference. Section summary. The ordering of examples in summarization affects the generation of hypotheses, and 2 approaches are presented: presenting descriptions randomly or grouping them by classes. The LLM generates concise summaries on standard datasets using a simple prompt, but requires a more explicit prompt on complex datasets. Using GPT-generated data descriptions consistently achieves better results, and cluster sampling improves the performance of the LLM by selecting a representative set of texts that generalize better.